Section 1 Introduction. We're going to discuss a key challenge in the field of large language models, LLMs, which is the issue of long context modeling. This problem is particularly difficult for transformer-based LLMs, as it leads to substantial computational and memory demands during the inference process, thereby increasing the cost of deployment. Many researchers have tried to address this issue by innovating the architecture of an LLM, but this approach has its own set of challenges. While some methods can significantly reduce computational and memory complexity, they often result in a noticeable drop in performance when dealing with long contexts. Instead of following this path, we've decided to tackle the long context problem from a fresh perspective: context compression. The idea behind context compression is that a piece of text can be represented in different lengths in an LLM, while still conveying the same information. For instance, if we use characters to represent the text, it might have a length of 2572. But if we represent it using words, we only need a length of 512 to express the same information. It's important to note that while character representation provides additional character-level information compared to word representation, this information is often unnecessary for most tasks unless character-level information is required, such as for spelling analysis. Therefore, the character representation of 2572 length is often wasteful of context slots without affecting the response accuracy. This leads us to question if there's a more compact representation that allows us to achieve the same goal with a shorter context. To explore this question, we propose the In-context Autoencoder, ICAE, an extension of our previous research on XPrompt, which aims to compress a long context into a short span of memory slots. The ICAE, like a typical autoencoder, consists of two parts: a learnable encoder adapted from the LLM with a parameter-efficient adapter, LoRa, for encoding a long context into a small number of memory slots, and a fixed decoder, which is the LLM itself, where the memory slots representing the original context are conditioned on to interact with prompts to accomplish various goals. To ensure that the ICAE performs well, we first pre-train it using both autoencoding and language modeling objectives so that it can learn to generate memory slots from which the decoder, i.e., the LLM, can recover the original context or perform continuation. The self-supervised pre-training with massive text data enables the ICAE to be well generalized, allowing the resulting memory slots to represent the original context more accurately and comprehensively. Then, we fine-tune the pre-trained ICAE on a small amount of Instruct data to align it for practical application scenarios by enhancing its generated memory slots interaction with various prompts for producing desirable responses. Our experiments show that the ICAE, when trained with our proposed pre-training and fine-tuning method, can effectively produce memory slots with 4 times context compression, which can be well conditioned on by the target LLM on behalf of the original context to respond to various prompts. Our contributions can be summarized as follows. 1. We explore context compression in an LLM and propose the In-context Autoencoder, ICAE, a simple yet effective and practical solution for addressing the long context challenge. Our approach generates a short span of compact and informative memory slots to represent a long context, which can be conditioned on by the LLM for various purposes. This either enables an LLM to express more information with the same context length or allows it to represent the same content with a shorter context, thereby enhancing the model's ability to handle long contexts while also helping reducing computational and memory overheads. Our work can be combined with other long context modeling approaches to further improve the handling of long contexts in an LLM. 2. To the best of our knowledge, we are the first to propose the pre-training and fine-tuning paradigm for context compression in LLMs. We observe that extensive self-supervised learning, i.e., autoencoding and language modeling, in the pre-training phase is very helpful to enhance the ICAE's capability to encode the original context into compressed memory slots. This pre-training process may share some analogies with humans enhancing their memory capacity through extensive memory training, which improves the brain's memory encoding capabilities, implying a novel perspective on working memory in the context of LLMs and artificial general intelligence, AGI. Section summary. Long context modeling is a challenge for large language models, LLMs, due to computation and memory overheads. Instead of architectural innovations, we propose context compression as a solution, using an in-context autoencoder, ICAE, to compress a long context into a small number of memory slots. Pre-training and fine-tuning the ICAE allows it to generate memory slots that effectively represent the original context, achieving 4 times context compression and enhancing the LLM's ability to handle long contexts. Our approach is the first to propose the pre-training and fine-tuning paradigm for context compression in LLMs. Section 2. In-context Autoencoder. We're going to discuss a model called the In-context Autoencoder, or ICAE for short. This model is similar to a standard autoencoder, which is a type of artificial neural network used for learning efficient codings of input data. The ICAE has two main parts, an encoder and a decoder. The ICAE works in a unique way, similar to the gisting and autocompressor models. It performs both encoding and decoding in an in-context manner, as shown in the provided figure. We suggest using a LoRa-adapted LLM, or language model, as the encoder for the ICAE. When the ICAE encodes a context, which is a sequence of words represented as W1, W2, WL, where L is the length of the sequence, it first adds K memory tokens, where K is much smaller than L, to the context. These memory tokens are represented as M1, M2, MK. The outputs of these memory tokens, represented as M1 tilde, M2 tilde, MK tilde, serve as the memory slots for the context. The ICAE encoder is quite efficient. It only adds a LoRa adapter and an embedding lookup for memory tokens compared to the target language model. We expect the memory slots to be conditioned on by the target language model on behalf of the original context. Therefore, we use the target language model itself as the decoder of the ICAE to ensure the compatibility of memory slots with the target language model. The main goal of the ICAE, like any autoencoder, is to restore the original input text from its produced memory slots. To indicate this autoencoding task, we add a special token, A, to the memory slots in the decoder. This pre-training objective doesn't require any extra annotation, so we can use a large amount of text data to train the ICAE. While this autoencoding pre-training provides a clear learning objective, its simplicity and focus on a single objective may not lead to the best generalization. To address this, we add an additional objective during the pre-training phase, text continuation. This self-supervised task is widely recognized to help language models learn more generalizable representations. In this task, we aim to predict the continuation of the context, represented as WL+1, WL+2, WL+n, from the memory slots. By integrating this task, the autoencoder can achieve better generalization and avoid over-reliance and overfitting to the autoencoding task. Section summary. The In-context Autoencoder, ICAE, is a lightweight model that consists of an encoder and a decoder. It uses a LoRa-adapted LLM as the encoder and the target LLM as the decoder to ensure compatibility. The ICAE has two pre-training objectives: autoencoding, which aims to restore the original input text from memory slots, and text continuation, which helps improve generalization by predicting the continuation of the context. Section 2.3 Instruct Fine-Tuning. We've developed a process called Instruct Fine-Tuning that comes into play after the initial pre-training phase. The memory slots created by the pre-trained In-context Autoencoder, ICAE, are designed to capture the original context. However, for language learning models, LLMs, the goal isn't just to remember or continue the context. Instead, we often use the context as a foundation for accurately responding to different prompts, which helps the model complete the tasks we want it to do. To improve how the memory slots from the ICAE interact with various prompts, we further fine-tune the ICAE using a dataset we've created called the Prompt with Long Context, PLC. This dataset, which we developed with the help of GPT-4, contains thousands of samples, each consisting of a context, a prompt, and a response. The fine-tuning process involves teaching the In-context Autoencoder to encode the context into memory slots. The decoder, or the target LLM, then uses these slots to generate a desired response based on a given prompt. The goal is to maximize the probability of producing the correct response given the memory slots and the prompt. In our initial study, we pre-trained the In-context Autoencoder using 1.6 billion tokens from a dataset called the pile. During this pre-training, we set the maximum token length, not including memory slots, to 512 for both the encoder and decoder of the ICAE. For the fine-tuning phase, we used the PLC dataset, which contains 240,000 training samples and 18,000 testing samples, each consisting of a context, a prompt, and a response. We tested the In-context Autoencoder's ability to compress context using a target LLM called Llama 7B. For the encoder of the ICAE, we applied a technique called LoRa to the query and value projections of the LLM's multi-head attention. In our standard setup, we set the memory slot length to 128 and the LoRa rank to 32. The resulting In-context Autoencoder adds only about 0.25% more learnable parameters to the target LLM. Section summary. After pre-training the In-context Autoencoder, ICAE, to generate memory slots representing the original context, we fine-tune it with the Prompt with Long Context, PLC, dataset to enhance its interaction with various prompts. The PLC dataset consists of thousands of context, prompt, response, samples, and the ICAE is fine-tuned to encode the context into memory slots, allowing the target language model, LLM, to produce a desirable response based on a given prompt. During pre-training, the ICAE is trained with 1.6 billion tokens from the pile, and for Instruct fine-tuning, the PLC dataset is used with 240K training samples and 18K testing samples. The resulting In-context Autoencoder adds only about 0.25% learnable parameters on top of the target LLM. Section 3.3.1 Autoencoding. We assessed the autoencoding capabilities of the pre-trained ICAE prior to any fine-tuning to see how well it could recreate the original context from the memory slots it generated. We used three metrics for this evaluation: BLEU, exact match, M, and cross-entropy loss. M is a measure of how much of the original context is exactly replicated. For instance, if half of a 512 token context is perfectly restored but the next token isn't, the M score would be 0.5. The results, based on the Llama 7B, showed that the ICAE had a very low overall loss, less than 0.05. This suggests that almost all the original context's information is preserved in the memory slots. When the context length is 300 or less, the ICAE can almost flawlessly recreate the original context, achieving nearly perfect BLEU and M scores. However, when the context length exceeds 400, both scores start to drop, implying that a 400 token context might be too much for the 128 token memory slots to handle. Interestingly, even with a 500 token context, the median BLEU score is still above 0.98, and the median M score is around 0.6. This means that the ICAE can perfectly recreate about the first 300 words of a 512-word context, further emphasizing the impressive performance of the memory slots. We also looked at how the memory size, denoted as K, affects the results. As the length of the memory slot decreases, the ICAE's ability to remember longer samples significantly worsens. For instance, when K is 128, the BLEU score can still exceed 95% for a 500 token context. However, for K values of 64 and 32, the BLEU scores are much lower, indicating that the ICAE struggles to perfectly retain the original context. This is also reflected in the loss curve, suggesting that achieving a compression ratio greater than 4x is quite challenging. We provided two specific examples of the ICAE restoring text with 128 token memory slots. The ICAE showed an interesting behavior when recreating the original context. For example, in the first example, the word partner was left out, and in the second, large pre-trained language model was restored as large pre-trained model. These errors are similar to the ones humans might make when trying to remember the same text. This implies that the model, like humans, selectively focuses on or ignores certain parts of the information during the memorization process based on its understanding. This aligns with our previous research findings. The stronger the base language learning model, LLM, the less it needs to memorize, and thus the less effort it requires. This is similar to human learning. Those with more knowledge tend to learn new things more easily, while those with less knowledge often resort to rote memorization. Based on this, it's likely that a more powerful LLM could support a higher compression ratio without significant loss of information. Section summary. The autoencoding performance of the pre-trained ICAE is evaluated using BLEU, exact match, M, and cross-entropy loss metrics. The ICAE demonstrates a low overall loss, indicating that the produced memory slots retain most of the original context information. However, as the context length increases beyond 400, both BLEU and M scores decline, suggesting that a context length of 400 may exceed the memory capacity of the 128 length memory slots. Additionally, as the memory slot length decreases, the ICAE's ability to memorize longer samples deteriorates, indicating a challenge in achieving over 4x compression. The model selectively emphasizes or neglects certain parts of the information during the memorization process, similar to how humans memorize text. A more powerful language model may support a higher compression ratio without significant forgetting. Section 3.3.2 Instruction following. We've been testing how well our integrated context and attention encoder, ICAE, follows instructions, using the PLC test set for evaluation. We compared the results of our system with those of GPT-4, a highly advanced language model, to see which one performed better. We also compared our system, which uses the Llama model to access the ICAE's memory slots, with two other popular language models, Alpaca and STABLELM7B. These models have 7 billion parameters and can access original contexts. Despite our ICAE's memory slot being only 128 in length, Llama significantly outperformed both Alpaca and STABLELM7B, with a win rate of 56.7% and 74.1% respectively. However, when compared to GPT-4, which we consider the gold standard, there was still a significant gap. In about 70% of the cases, our system underperformed compared to GPT-4's results. We also fine-tuned our Llama model using the same training data and modules as the ICAE to make a fair comparison. The results showed that the 128 length memory slots underperformed original contexts in about 7.9% of cases. This was expected, as original contexts have complete information and thus their performance can be considered as the upper limit for the ICAE's performance. However, considering that the ICAE achieves nearly a 4 times context compression and about 75% of cases can perform better than or as well as original contexts, its performance is still promising. We also tested the ICAE's memory slots with lengths of 64 and 256. The performance of the 256 length memory was significantly closer to that of original contexts than the 128 length memory, but when the length was 64, the performance worsened due to excessive compression and information loss. We also compared the performance of ICAE models with different memory slot lengths. The results confirmed our observation. The higher the compression ratio, the more difficult it is to ensure the quality of the compression. However, a larger compression ratio doesn't always result in worse performance. For example, a well-trained IC's 8 times compression can rival a less effective compressor's 4 times compression results. We also compared the outputs generated by the pre-trained and non-pre-trained ICAE. The pre-trained ICAE suffered significantly less from hallucination and responded to prompts more accurately than the non-pre-trained counterpart. Finally, we compared the effect of the ICAE's 128 length memory slots with a summary produced by GPT-4. Memory slots significantly outperformed summaries under the same context length, with a 1.2 win-lose ratio. We believe that with larger scale pre-training, the performance of memory should improve even further. Section summary. The performance of the ICAE in following instructions was evaluated using the PLC test set, comparing it to the GPT-4. The results showed that the ICAE with 128 length memory slots outperformed Alpaca and STABLELM7B, but still had a significant gap compared to the GPT-4. Fine-tuning the Llama 7B with access to original contexts showed that the 128 length memory slots underperformed, but considering the 4 times context compression achieved by the ICAE, its performance was still promising. The performance of the ICAE's memory slots with lengths of 64 and 256 were also evaluated, with the 256 length memory slots performing closer to original contexts. The impact of memory length on results was further analyzed, showing that a higher compression ratio made it more difficult to guarantee compression quality. The pre-trained ICAE showed significantly better performance than the non-pre-trained counterpart, demonstrating the importance of pre-training for context compression. Memory slots were found to outperform summaries in terms of compactness and informativeness, but further improvements are expected with larger scale pre-training. Section: Scaling. We found that our proposed method, the ICAE, can indeed compress context through the use of memory slots. Even though our initial experiments were conducted on a small scale due to limited computing resources, the ICAE showed promising results in terms of context compression. We're interested in understanding the limits of this compression and whether these limits are tied to the size of the model. We're considering scaling up both the ICAE and the backbone language model, and using larger amounts of data for pre-training, potentially in the hundreds of billions or even trillions of tokens. As we've previously discussed, a more powerful language model might require less working memory to model a context, and we believe this could also apply to context compression. Investigating the scaling law for compression limits could provide valuable insights for balancing context length and generation quality in real-world applications. We've also noticed that after fine-tuning our model on our PLC dataset, our memory slots actually performed better than both Alpaca and STABLELM when using the original context. This suggests that the ICAE, when specialized for specific data or tasks, could potentially match or even surpass the original context. This is similar to how smaller models might struggle to compete with larger models in all areas, but when specialized, they can certainly hold their own or even outperform larger models in certain aspects. We believe this could be an exciting area of research that could have practical applications in model deployment. By combining autoencoding and language model pre-training with fine-tuning, our memory slots can be effectively generalized to interact with prompts on behalf of the original context. However, our approach's generalization capabilities are still limited, and the memory slots are not yet fully equivalent to the original text. For instance, we found that freely combining memory slots doesn't have the same effect as combining their corresponding original contexts. This is because these usage patterns were not included in our training data, and the ICAE is not yet fully capable of generalizing to extrapolate these unseen patterns. However, we don't recommend using a recursive training approach during the pre-training phase, as it's computationally expensive and not conducive to scalable pre-training. Instead, we suggest adapting the model to more use cases during the alignment, fine-tuning phase, where only a small number of training samples are needed for each use case. This allows the model to efficiently adapt to different scenarios. We plan to explore this further in our future work. Section summary. The authors found that their proposed ICAE model can achieve context compression through memory slots, demonstrating promising performance even on a small-scale model. They suggest that exploring the scaling law for compression limits and specializing the ICAE for specific data tasks could be meaningful for practical applications. While their memory slots can be well generalized to interact with prompts, they are not yet fully equivalent to the original text, and further research is needed to improve generalization capabilities. Section 5. Related work. We're going to discuss some related work in the field of context compression, a relatively new area of research in the world of large language models, LLMs. This field aims to tackle the problem of lengthy contexts from a unique angle. As far as we're aware, there hasn't been a lot of research in this area yet. Two closely related fields are prompt compression and context distillation. For example, one method that has been proposed involves learning compact soft prompts that mimic the original natural language prompt. This is achieved by optimizing a measure of difference called the KL divergence. However, this method is computationally expensive because it requires a process called backpropagation for each new prompt in order to learn and obtain the compressed prompt. This limitation makes it difficult to apply widely. Another approach, known as GIST, compresses prompts by fine-tuning an LLM in a way similar to our method. The resulting model can generate a number of GIST tokens as a compressed version of a prompt, which are similar to what we call memory slots. However, this method is only suitable for compressing short prompts and doesn't address the main problem of long contexts. Additionally, this method requires fine-tuning the LLM, and the GIST tokens produced need to be used within a specially tuned LLM, which doesn't seem to be compatible with the original LLM. A recent work that is related to ours proposed autocompressors, which recursively compress long text into summary vectors. Like the previous method, the LLM needs to be fine-tuned to work with these generated summary vectors, and its training is complex because it involves recursive compression. In contrast, we propose a simple, direct, and scalable method for generating memory slots that can be used in the original LLM with different prompts for various purposes. Our approach is much more efficient in terms of parameters, adding only 0.25% additional parameters, i.e., LoRa, for tuning. Section summary. There has been limited research on context compression in the era of large language models, LLMs, with related work focusing on prompt compression and context distillation. Previous methods have high computational costs and are limited to compressing short prompts, not addressing the issue of long contexts. Our approach, in contrast, is a simple and scalable method that generates memory slots for use in the original LLM with different prompts, adding only 0.25% parameters for tuning.